What's up, everybody? Welcome back for another chemistry lesson with Mr. A. Today we are learning about mole ratios. I'm sorry, relationships, and then we're going to learn about mole mass relationships. So these two topics connect back to our mole ratios. We're going to start off with the mole to mole relationships, and then we'll work our way to the mole mass relationships. Now, in order to do these, we need to understand mole ratios, and then we need to remember from last semester how to convert between moles of a substance to grams of a substance. And we'll revisit that in just a little bit. So to start off today, let's start off with an example, again, just a little refresher maybe, of how we can find our mole ratios. So let's take an example equation right here. Zinc reacting with hydrochloric acid to form zinc chloride and hydrogen gas. Now, remember when we're given a chemical equation, the first thing we should do is balance it. And looking at this, we can see on the left side, 1 zinc, 1 hydrogen, 1 chlorine. On the right side, 1 zinc, 2 hydrogens, and 2 chlorines. So you can see on the left side here, hydrogen and chlorine, both we need 1 more of each one. Very convenient for us because they're together in HCl on the left side. So all we need to do is put make a little bit of space here, put a 2 coefficient, and we have a nice and balanced chemical equation. Quick and easy. Just the way I like it. All right. So now that we've balanced our chemical equation, we can actually make our mole ratios. And remember, for our mole ratios, those are relationships between two components in a given chemical reaction. All right, so it's the relationship between two components in a given chemical reaction. Remember, we use the mole amounts. Important that they're the mole amounts, and these are from the coefficients of the balanced chemical equation. All right, so that's very important. There are two things that are very important there. It's the mole amounts, and it's the balanced chemical equation, where we get these mole amounts, again, from the coefficients. All right, so just remembering that information from our last lesson, let's go ahead and copy this down here, if I can figure out how to do that. Boom. It's like magic. All right, so let's make our mole ratios. So in order to make our mole ratios, we start with our, let's start with the leftmost component, so zinc. And we're going to make a relationship between zinc and HCl, zinc and ZnCl2, zinc and hydrogen gas. All right, that's going to be our first set of mole ratios that we make. So in all of these, zinc, looking at zinc, its coefficient will doesn't have a coefficient. So since it does not have a coefficient, we know that really means there's 1 mole of zinc. Right, so all of these ratios are making with zinc, we know it's only 1 mole of zinc. Now, all we need to do is find the bottom half of each of these mole ratios. So again, we do that by looking at the coefficients of our given components. So for moles of HCl, I look at its coefficient and it's 2. So 2 moles of HCl. For zinc chloride, there's none, so we know that means there's really 1. And the same thing goes for hydrogen gas, H2, there's 1 mole H2, and we just made 3 mole ratios there. Wonderful. So let's go ahead and erase some of this, clear it off nicely. So now we finish with all the mole relationships with zinc. So we move on to the next component to the right, HCl, and we make relationships with everything else left to the right. So HCl to zinc chloride and to hydrogen gas, H2. So again, looking at the coefficients, all these have moles of HCl. And we can know from the coefficients that there's 2 moles of HCl. So now again, to complete these mole ratios, we look at the coefficients of the other components. So for zinc chloride, coefficient is empty, so it's 1. And the same thing again for moles of hydrogen gas, 1. Okay, so now we're done with the relationships between HCl and the other components. Again, we don't have to make a relationship between HCl and zinc because we already have that one. All right, so again, we only work from left to right, and that way we only get the mole ratios that we need, and we don't repeat any information. It's important to remember, though, that these mole ratios can also be written in the reverse form. So for example, right here, 2 moles of HCl for every 1 mole of zinc chloride. I can also flip that and say 1 mole of zinc chloride for every 2 moles of HCl. So technically you can double the amount of mole ratios that we have if you rewrite them in that flipped version. And we're going to learn why you want to actually flip those today. Again, it's just going to be for us to use our dimensional analysis to convert units to the units that we desire in any given problem. But we'll learn that in just a bit. Just finishing off here, we have one more ratio to make between zinc chloride and hydrogen gas. And we should remember that there's 1 mole of zinc chloride for 1 mole of hydrogen gas. And there we go. So now we've written all of the mole ratios for this specific problem. All right, so now that we reviewed mole ratios, let's get into our mole-mole relationships. Okay, so mole-mole relationships, what these questions are going to be asking us is kind of like how I was talking about before with the recipes. Instead of making a dozen cookies, making 2 dozen cookies, However, in this case, we're talking about chemical components. So instead of 1 mole of zinc, let's say we had 500 moles of zinc. How many moles of HCl will we need? So let's get some questions, some example questions for us there, and just kind of see what this looks like. So let me copy this equation again. Let's keep working with this equation. And we're going to refer to the mole ratios that we've made here previously. Let's copy that, paste it. This is pretty magical stuff. Pretty awesome, I know. Anyways, so some questions you might get asked when dealing with mole-to-mole relationships, as I was saying. Let's put number 1. If we had, I don't know, 5.8 moles of zinc, how many moles of HCl would we need for this reaction? All right, so this might be an example of a question you could receive. So what this question is saying is that we have 5.8 moles of zinc, and we want to make this specific reaction take place. Right? We have 5.8 moles of zinc now instead of just 1. So if we have 5.8 moles of zinc, how many moles of HCl do we need to make this reaction take place? We know from this equation right here, well, if we had 1 mole of zinc, we would need 2 moles of HCl. And that's from our wonderful mole ratio right here, right? 1 mole of zinc for 2 moles of HCl in order to make this reaction take place. We know that information. However, in our question, we're no longer talking about 1 mole of zinc, we're talking about 5.8 moles of zinc. So let's write down that information right here. 5.8 moles of zinc. So, in order to find out how many moles of HCl we need to make this reaction take place, what we're going to do is find a relationship between moles of zinc and moles of HCl. And we've already made that relationship, or found that relationship, back here with the mole ratio between moles of zinc and moles of HCl. So let's go ahead and copy this down here. Some important information for us. Okay, so there's our mole ratio, between zinc and HCl. So that's going to help us get to where we need. Now, where do we need to get to? Good question. Well, if we treat this like a dimensional analysis problem, we need to first determine what units we're starting in, and what units we want to end up in. So if we look at the question, what units are we starting in? Well, based on the given information, you can see we're starting in units of moles of zinc. Right? We're told that we have 5.8 moles of zinc. Looking further in the question, we can see where we want to end up with. We want to end up with moles of HCl. So now we know where we want to start. and where we want to end. We'll start with moles of zinc, what we're given, and we're going to end with moles of HCl. How many moles of HCl do we need to make this reaction take place? So in our question, in our work here rather, we're going to treat, wrong color, we're going to treat moles of zinc as a given unit, and then we're also going to treat moles of HCl as a separate unit. And then we're just going to use dimensional analysis to convert between units of moles of zinc to units of moles of HCl. So we have this mole ratio right here, and we're going to do that, or we're going to use that rather in our dimensional analysis up above. So we can see, or we know rather, we want to end up with moles of HCl. So that means that units of moles of zinc should cancel out. So in order to cancel out these units of moles of zinc, I need moles of zinc down here. Like I said before, we want to end up with moles of HCl. So that means in our conversion factor, I need moles of HCl in the numerator. So instead of writing our mole ratio this way, we're going to use the flipped version. So flipping that over, we have 2 moles of HCl over 1 mole of zinc. Just keeping that color coded there for us. All right, so all we did was just flip this mole ratio to use it in a form that's helpful for us. So that's just going to go up there. So we have 2 moles of HCl and 1 mole of zinc. All right, so we're just utilizing our mole ratio. And if you do the math here, you'll see that units of moles of zinc cancel out, and we'll be left in units of moles of HCl. So just multiply across 5.8 times 2 usually is, oh, I don't know, 11.6. Sounds good to me. And not worrying about sig figs, we'll just leave that answer. And so we found out that if we start with 5.8 moles of zinc, we need 11.6 moles of HCl in order to make this reaction take place. Okay, so that's how we're going to start utilizing these mole ratios here. Again, we just made relationships between the different mole values of a given reaction to take place, and then we just kind of expanded on it. Instead of 1 mole of zinc, we have 5.8 moles. So we just had to figure out, well, if we have 5.8 moles, we need 11.6 moles to make this same reaction take place, just a little bit more. All right, so that is the mole-to-mole relationship. Okay, so I have some steps here. This one. There we go. So these steps here should be able to help you kind of follow that same process that we just did in this example. All right, so steps for calculating number of moles of reactants and or products in chemical reactions. We started with the balance equation, right? Up here we have our balance equation. 2, we use the balance equation to set up appropriate mole ratios. We did that up here. And then 3, use the mole ratios to calculate the number of moles of the desired reactant or product, right? Based on our question, we started with moles of zinc, wanted to end up in moles of HCl. So we use this mole ratio right here to solve for the desired amount of reactant or product. Okay, so these are the steps here. And just remember, this is just a dimensional analysis problem applied to chemistry. Right? We've used dimensional analysis before, just not as applied to chemistry as this is. Okay, so let's do a couple more example problems, and then we'll move on to mole mass relationships. Okay, so let me see here. Let's get a different equation. Why not? Something a little bit more fun, right? How about the reaction between calcium hydroxide and phosphoric acid to form calcium phosphate. Uh-oh, running out of room here. Let's see if I can salvage this. Whoa. And water. Okay, so this is our new equation here. Might not have enough space. Let's see. Come on. That's pretty good. All right. So now that we have an equation, first thing we should do is balance that out. So just looking over on the left and right side, we have 1 calcium, we have 3 hydrogens, and now one thing to do in these balanced equations, one easy, maybe something that makes it a little bit easier or a little bit more organized to keep track of, is keeping polyatomic ions together. So on the left side, on our reactant side, we have 2 polyatomic ions, hydroxide and phosphate. So what I'm going to do is keep those together. So we have 2 hydroxides and 1 phosphate. Now the reason I do this is because there's actually 2 places where hydrogen is and where oxygen is. So it becomes a little bit harder to consider balancing those when they're in separate locations. However, by putting them together in their polyatomic ions, hopefully it'll make this a little bit easier. On the right side now, we have 3 calciums, 2 phosphate. Now, with H2O. H2O really is HOH. So something you kind of have to remember to make this trick work is that H2O is really H and OH. So we have 1 hydrogen and we have 1 hydroxide there. So now we can balance this equation by grouping together the polyatomic ions properly. All right, so let us look over here. We have, well, looks like everything's unbalanced, huh? So let's start off by looking at, how about the calciums? Okay, we have 3 here and 1 here. So let's go ahead and put a 3 in front of calcium hydroxide, which will make must have 3 calciums, and that's also going to change the number of hydroxides to 3 times 2, 6 hydroxides. Okay, so that's good with calcium. Let's move on to phosphate now. Phosphate on the right side, there's 2. On the left side, there's 1. So I need to put a 2 in front of our phosphoric acid to give us 2 phosphates on the left side. This is also going to change the number of hydrogens on the left side. 2 times 3 will give us 6 hydrogens. Okay, so now we've balanced the calcium, right? So that's good. And phosphates. The only thing left unbalanced are hydrogens and oxygens. Now, on the left side, we have 6 hydrogens, 6 hydroxides, and 6 hydrogens. On the right side, we only have 1 of each. But hydrogen and hydroxide are together in H2O. We have 1 of each from H2O. So if we put a 6 here in front of H2O, that's going to change the number of hydrogens to 6 and the number of hydroxides to 6, which means now our equation is nice and balanced. As easy as that, huh? Oh yeah, good stuff. All right, so now that we have a balanced equation, let us go ahead and start getting down our mole ratios. All right, so I'm just going to go through the process that you should be going through. Once you become more comfortable with these mole ratios, mole relationships and the mole ratios, you might not necessarily have to write every single possible mole ratio that's possible for this equation here. You only have to use the ones that are needed. But to begin with, it's a good practice to write down all the different possible mole ratios. Again, in order to do that, we're going to start with the leftmost component, calcium hydroxide, and make a relationship between everything to the right, like so. Without going into too much detail again, just remembering that to make the mole ratios, we look at the coefficients for each component. So we have 3 moles of calcium hydroxide for all of these. Barely fit in there. All right, 3 moles of each. And then looking at the next one, we have H3PO4, 2. Okay, so 2 moles H3PO4. At the next one, there's no coefficients, so I know that means there's 1 mole of calcium phosphate. And looking at the last one, 6 moles of good old-fashioned water. All right, so now we finished making those mole ratios for calcium hydroxide. Now I'm going to start with phosphoric acid and work our way towards the right. So in all of these, we have 2 moles of H3PO4. I did record this while you were in class, and I had off periods. So if you hear the bell, that's why. Anyways, continuing on, looking at the next component, calcium phosphate, 1 mole. The last component, H2O, 6 of those. Righty, that looks pretty good. And now for the last mole ratio, looking at calcium phosphate, making a relationship with water, we know that there's 1 mole of calcium phosphate, and the coefficient is 6 moles of H2O. And now we are done with our mole ratios. So we've written down every mole ratio. We found every relationship between any 2 given components. So we're good to go for calculating any of these mole relationships. So with that done, let's go ahead and move on to our example questions with this reaction here. Let's go ahead and copy that. Paste it down here to start off with. And let's put back our rules here. Right here, nice corner. Action, boom, boom. All right. Looking pretty nice. Oh. Don't know what happened there. 1 second. Okay, I guess I can't move that. That's not a big deal. Anyways, in this steps here, we have done step 1, balance the equation. And up here, we've done step 2. Use the balance equation to set up the appropriate mole ratios. Again, that appropriate, like I was saying before, once you get more comfortable with this, you only need to make the mole ratios that you need based on the question. However, as we're starting, I suggest you make all of these mole ratios, just for good practice. So step 3 now, use the mole ratios to calculate the number of moles of the desired reactant or product. Well, we need to have a question to solve in order to do step 3. So let's look at our example question here. Let's say how many moles of, let's do water. How many moles of H2O could be produced if we have, I don't know, 9.7 moles of calcium hydroxide. That sounds good to me. All right, so now we're given our example question. We can figure out what we need to figure out. So let us go through the question and see what's given to us. So first thing I can see here is that we're asking how many moles of H2O. So I know that our desired unit, or where we want to end up with, is moles of H2O. All right, so I'll highlight H2O in the reaction too, just to make sure that we're clear on everything. Then I keep going through, blah, blah, and I see 9.7 moles of calcium hydroxide. So I know we're starting with 9.7 moles of calcium hydroxide. And I know we want to end up with number of moles of water, H2O. So we have a starting point and an ending point. Wonderful. So like I said, we're starting with 9.7 moles of calcium hydroxide. And I think that is a blue highlighter. And we want to end up with moles of H2O. Okay, so what we need to do is find a mole ratio that has a relationship between calcium hydroxide and H2O. If we go back to our mole ratios, we could find that relationship in this mole ratio right here. It tells us that there's 3 moles of calcium hydroxide for every 6 moles of H2O. And just kind of trying to use our lingo, our chemistry lingo. Remember, calcium hydroxide is a reactant and H2O is a product. So a more proper way to read this is that 3 moles of calcium hydroxide are needed to produce 6 moles of H2O. And that kind of connects to our question here. It says how many moles of H2O could be produced if we have 9.7 moles of calcium hydroxide. And that's just kind of reiterating the fact that H2O is a product, while calcium hydroxide is a reactant. Okay, and this is going to become a little bit more important later on in the chapter, so I'll probably emphasize the language a little bit more then. But for right now, it's good to just kind of remember. All right, so like we said, we have this mole ratio right here. And what I'll do is I'll copy this over, hopefully, for us to use. Oops, let's copy and paste it. All right, so there is our mole ratio that we're going to use. Keeping our highlighting, color coding this nice and nice. Boom, boom. There we go. So what we want to do is end up with moles of H2O in this question. So that means I need moles of H2O in the numerator. And we're starting with units of moles of calcium hydroxide. So we want to cancel that. So we need moles of calcium hydroxide in the denominator. Let's just go ahead and highlight that. Okay. So just using this mole ratio here, just keeping the numbers with the proper units. There's 6 moles of H2O for 3 moles of calcium hydroxide. We can look at the problem. I'll finish after this video right here. So we look at the problem, and we can see that units of calcium hydroxide will cancel out, and we'll be left with units of H2O, which is exactly what we want. So we go ahead and do the math there. 9.7. So this is the math you should be doing. 9.7 times 6 divided by 3. And if we do that, we will get 19.4 moles of H2O. Again, I'm not worried about sig figs right now, just learning the process of our multiple ratios. All right, so in the end, to answer this question, if we have 9.7 moles of calcium hydroxide, we are able to produce 19.4 moles of H2O. And we're able to figure that out because of our mole ratios from our balanced equation. Very nice. All right. So for you to practice at home and to bring to class, whenever the next class is, let's copy this if I can. Oh my gosh. No. This darn technology. Let's try this one more time. Oh. Looks like I win again, technology. Anyways, let's just put that there. Clean this up a bit. Boom, 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 boom. All right. So for you to try at home, before you continue, let's see, a couple examples, maybe one, two, three questions, maybe, let's say. Okay, so if, let's see, 6.7 moles of H3PO4 are reacting, how many moles of calcium phosphate can be produced? If 7.3 moles of calcium hydroxide are in the reaction, how many moles of H3PO4 are also needed? And 3, if 10.1 moles of H2O are produced, how many moles of calcium phosphate are also produced? All right, so these 3 sample questions right here, go ahead and do these before moving on to the next video. I'm going to make a separate video for the mole mass relationships. So a little bit of a continuation to this video. So go ahead and do these 3 examples before you move on to that video, and bring these to our next class. And we'll go over it at the beginning of class. Hope you enjoyed the video. Hope this has been helpful for you. Hope you enjoyed. Make sure, as they say on the YouTube, to like, subscribe. Let me even write that down right here. Like, subscribe, and hit that bell if you feel so inclined. And because, well, you need to keep up with your lessons, of course. It's been a pleasure, as always. Till next time.